Comparison of connecting rod structural analysis with different materials. And Sreenivasa Babu. Engineering Department. Shinas College of Technology. Sultanate of Oman. Abstract, connecting rod is an important link connects to the piston and crankshaft in transferring the power. Due to its importance, an attempt is made in evaluating the displacements, stresses and von Mises stress of the model under different loading conditions at crank end and pin end. Weight reduction is also carried to achieve the material savings by shape optimization, and the analysis is continued. A typical model is chosen with 1.972% in weight reduction and a 2.53% increase in the von Mises stress due to shape optimization. The analyzed von Mises stresses are well in good understanding with the maximum limits of the material maximum stresses. Keywords: von Mises stress, weight reduction, shape optimization, structural analysis. 1. Introduction. The crankshaft conrod mechanism transforms reciprocative motion to rotational motion. The conrod connects the piston to the crankshaft to transfer combustion pressure to the crank pin. There are bearing portions at both ends. The piston side is called the small end, and the crankshaft side, the big end. Connecting rods are commonly made from cast aluminum alloys to withstand dynamic stresses due from the combustion and piston movement. A typical focus is needed in evaluating the von Mises stress with different materials for comparison analysis. At instance, 4 different materials are chosen for the comparison purpose and properties are given from Table 1.1. 2. Literature survey. Connecting rod is an important component that needs a typical analysis towards its structural stability under dynamic conditions. 2. It is also critical to maintain an optimum weight to strength ratio to sustain inertial loads. Shape optimization is critically needed to reduce inertial load, thus by minimizing the internal stresses during dynamic condition. Loading conditions are chosen 1 at the crank end and pin end to analyze the von Mises stresses, and shape optimization is carried randomly to reduce the weight of the component. In the analysis, the authors emphasized on the calculation of the dimensions of the component and needs to be focused more on shape optimization and weight reduction. In this project, the shape optimization is chosen randomly, and different materials like alloy steel, titanium alloy, Ti6Al4V, 1044 carbon steel and aluminum alloy, A6061 are chosen for structural analysis for the best suitable material with respect to cost and availability. 3. Model development and strategy. A typical connecting rod is modeled using AutoCAD software and imported in the analysis software ANSYS 08 used to simulate engineering models to extract displacements and stresses. A solid brick element has chosen for its meshing element, and different loading conditions, tension and compression, were considered at the crank end and pin end. At the crank end 10.11 MPa in tension and 20.67 MPa in compression is taken, while other end is in fixed boundary condition. Similarly, at the pin end 22.24 MPa in tension and 20.17 MPa in compression is taken, and other end is in fixed boundary condition 1. 4. Results and discussions. The connecting rod analysis is performed for its deformation, stress, and von Mises stress with different materials under typical loading conditions. The results are tabulated and compared its dynamic stability. 5. Conclusions and future scope. A noticeable 1.972% in weight reduction and a 2.53% increase in the von Mises stress due to shape optimization is observed. Even the deformations of aluminum alloy material are more, and it can be ignored based on the low weight advantage. Further, similar models can be analyzed for its eigenbuckling and modal analysis to find its natural and forced frequencies. Shape optimization is also can be enhanced based on the strength considerations.